Today I am going to talk on bipolar junction transistor. In short, it is called BJT. So what is a transistor? It is made up of three extrinsic semiconductors connected back to back, thus making two junctions. One is called emitter base junction and other is called base collector junction. These three regions are named as emitter base collector, and depending upon the extrinsic semiconductor nature, it can be of PNP or NPN. So actually we are going to first know what is emitter and what is collector and what is base. So emitter is that portion of the transistor which is heavily doped, and it is larger than the size of the base but smaller than the collector. And collector is not heavily doped, it is moderately doped, but biggest among emitter, base and collector. And base is made thin, very thin, and it is sandwiched by in between emitter and collector. So these are the three regions, and here first we can look the current components of PNP transistor. Okay, if the question becomes NPN, just reverse those direction of the current as shown in this figure. But let us first know, or let us first calculate the current component of PNP transistor. Now here you can see that P. What is P type? P type has majority holes and N type has majority electrons. So there, if you connect for the normal operation of transistor, what is the normal operation? The normal operation or normal requirement of transistor, or the use of the transistor, is to amplify the voltage. So amplify the voltage, amplify the current, amplify the power, whatever you need. So it is used to amplify something. So for this normal purpose, the emitter base junction is made. This junction is made forward biased, this is made forward biased, and this junction is made reverse biased. So you can see here, as it is P, so it is connected with positive and base is connected to negative. So base is negative, means N type is negative, so it is forward biased junction. This junction is made forward biased, and similarly reverse bias connection, you should connect P type with the negative of the battery. So it is connected like that with the V2 battery. Now since it is positive connected, emitter is P type and it is connected with positive terminal of the battery V1, so the majority holes should be pushed through the junction to cross the junction and get entered into the base area. So that constitute a current IEP, P for positive. And similarly the negative terminal, this negative terminal connected with the base will repel the all majority electrons at this base region. So they will cross the junction in this direction, so a current will follow along opposite direction, which is IEN, that is due to the negative current. So both of them will constitute the emitter current, which is written here. Similarly, in collector, what you can see is that the collector is reverse biased, so there is no majority flow, but there should be minority flows, which is known as reverse saturation current. For this, the negative charges, that is electrons, are minority at P side. Similarly, holes are minority at N side. So as negative is connected with the negative terminal is collector, so the holes will be attracted into this direction, so it will constitute a hole current, ICOP, that is reverse saturation current due to hole. And similarly reverse saturation current due to electrons will also follow. and this one is the main component of current of collector, which is IC1P. What is that? Now first the holes are coming from the P type, that is emitter, and it crosses the junction due to the forward biasing voltage, as I have discussed, and those which are recombined with the electrons in the N type region, that is IE minus IC1P, and the rest of the charges which is not recombined with the negative charges, those will follow the same path and get entered to the collector region. That component of the positive current, that is hole current, is called IC1P. So the rest of the current IEP minus IC1P is the recombination current, which will go to the ground. So the direction is like that. So the current components of the collector are three: IC1P and two minority currents. So it is written over here. And the base current, you have already we have already discussed that. That is base current. You can see here the current entered to the region is IEP minus IC1P, it is recombination current, as well as the currents are going from the base to the collector, ICOP and ICON, so that will be minused, and similarly IN is entering the base region. So four types of currents are there. So remember the signs. This is positive, the recombination current, because it is entering to the base region according to the KCL sign law, and the current IN also entering to the base region from the emitter, so it is again positive, but those two minority currents are flowing out, so those are negative, and by rearranging those you can write C IE minus IC. So IE is equal to IB plus IC, that is nothing but the charge conservation rule, that is the KCL law. If you consider the transistor as a point, so emitter current is entering here, this current, and it is distributed in two components as emitter and base and collector currents. So the circuit symbols are like this. This is PNP and this is NPN, the two types of circuit symbol. The arrows are differentiating two transistors, whether it is PNP or the ANPN, the arrow at the emitter junction, emitter base junction. Okay. Now there are certain modes of operation of the transistor. There are three types of modes: CBC, that is common base, common emitter and common collector modes. So let me first discuss the common base mode, where we can see that base is made ground. That is why it is called common base or grounded base also. Okay, so common base means grounded base, that is its potential is 0. Now emitter is here in the picture. You can see we have taken the NPN transistor. Okay, so this is N type, this is P type base, and collector is N type. So collector is made reverse biased by connecting positive terminal to the N type, and similarly N type connected to the negative terminal of the input battery VEE, it is made positive forward biased. So you can see here, if you calculate the KVL, apply KVL in this loop, you can write VEB is equal to minus of VEE. So it is negative. So emitter is negative. VEB negative means emitter is negative with respect to base, so it is forward biased. And similarly VCB is positive VCC, that is collector is positive with respect to base, which means that JC, that is the collector junction, is reverse biased. So normal operation, for normal operation we have to connect like this in CV mode. And now for CE mode, you can find here the connection is here, emitter is grounded, and all connections are made keeping in mind the forward and reverse bias, and you can verify this from these equations also. And this is very interesting. You can see VB is simple. VB is equal to VBB, so it is positive, so base is positive with respect to emitter. What is base? Base is your p type, and emitter is n type, and collector is also n type. So base should be positive with respect to the emitter, so that forward bias connection is prevailed in the JE, that is the emitter junction. And for collector junction, collector base junction, we should have the reverse bias connection. So in this picture you can see the collector base junction potential, so you have to find that using KVL. KVL in this loop, VCB. Now look this way, this is the loop which here is considered this one. So three potentials are there, VCB, VB and VCE. So algebraic sum of them will be 0 according to KVL law. So this will give you VCB is equal to VC minus VB. So VC is again VCC and VB is VBB. So if you make VCC greater than VBB, then this will be positive. So collector will be positive with respect to base, which we need. So that is why you can see for normal operation VCC is made more powerful than the VBB battery for CE mode. And you can set the collector base junction as reverse biased if you made weak the VCC battery with respect to the VBB battery, and unbiased if you take two equal power batteries, and then the collector base junction should be unbiased because VCB should be 0. That means collector and base are equal in potential. Similarly, common collector mode is explained here. It is a common collector amplifier circuit. So I'll suggest you to come back to this connection, or rather you can, okay, I'm just discussing here. See, this is looking like common emitter, no, but not, because there is a resistance connected from emitter to ground. So the zero potential is not the emitter point, it is another different point. So this is not the common emitter connection. So what is this? We have to understand first this thing. So let us not here it is AC signal. Let us not apply this and just apply VBB, VCC. Just do the KVL thing, and you should write VCG, that is collector to ground potential, is equal to VCC. That it is written in the equation number 1. And now switch on this AC generator, then it will constitute an AC component of current. So there should be an AC component of the potential also in between collector and ground point. So that component of AC signal should be VCG, but according to KVL that should be is equal to VCC, because in that loop you can consider it. Now VCG is equal to VCC, so both of them will cancel and results in VCG is equal to 0. That V is not the DC V, that is AC voltage between the collector and ground, which is 0. That means collector is grounded. Collector and ground are at same potential with respect to AC. So that is why this connection is called common collector amplifier circuit, not the common emitter, because emitter is not grounded, but collector is not visually grounded, but effectively collector is grounded with respect to the AC connection. So the common collector amplifier name comes here. Now next move on. to the next topic, which is static characteristic of a transistor. And here we will assume the NPN transistor, and first we take the CV mode, and you know the CV mode, the input voltage and current are IC and IB, IE and VEB. You can consider the picture which I have shown, and the output voltage is VCB and output current is IC. So the input voltage versus input current picture is called input characteristic. And here you can see there is a cut-in voltage, because in CEB mode the emitter base junction is in forward bias, so forward bias junction will follow the forward bias PN junction curve. So current will be 0 from certain point up to certain point, then at a certain point the current starts flow, and this point is called cut-in voltage. You know from diode characteristic, that is purely diode characteristic, but there is a difference. The graph is drawn with respect to the parameter VCB as a constant, that is the collector base voltage, that is the output voltage. You can see here, you can see collector base voltage is the output voltage, this one VEB is the input voltage, IE is the input current which is flowing out, that is negative, and IC collector current is the output current which is flowing in, that is positive, and VCB is positive again, but VEB is negative because negative terminal is connected to emitter. So all these symbols are taken care of here in the graph. Yes, you can see. So if you make constant the output voltage, that is VCB, at 2 volt, then the graph will follow this. If you make it larger, that is 6 volt, then the graph will shift it towards up. That is due to the early effect. What is that early effect? I will discuss it later. Early effect, that effect for which the yes, let us discuss at this point. First, early effect. Early effect is the modification of the depletion region and consequent change in the effective electrical width of the base region. See, emitter, base and collector is drawn here, and this is your emitter base junction JE, and this is your collector base junction JC. But in the collector base junction there is a depletion region, so effective electrical width of base initially. But if you increase the voltage VCB, that is collector voltage with respect to base is increased, then the reverse bias voltage increased, then the depletion region will increase. So depletion region initially was at this up to this point, but finally if you increase VCB, then depletion region will be spread in more to the base region. So effective electrical width, that is available electrical width of the base where the majority carriers will stay, will be decreased. So the base current should also decrease, because the recombination component of the current coming from the emitter region will decrease, because the effective width of the base decreased, and as a matter of fact the recombination chance of those current carriers will be decreased again. So that will decrease the net component of the recombination current in the base region, and you know the base current, the main component of the base current is the recombination current. So IB will decrease, but IE will increase, because effective electrical width of base is decreased due to the increase in collector base voltage. So the charge carrier concentration in the base region is increased, and emitter has that component, so emitter current will increase, as well as recombination current as the cause of or the effect of the recombination current getting decreased, the collector current will increase. So the main effect in 2 points of the early effect is that if you increase the reverse bias voltage at the output terminal, it will increase IE and IC but decrease IB. So you can see here in the input characteristic of the CB mode, the VCB, that is reverse bias voltage, is increased from 2 to 6, and the emitter current is also increased from here to there at a particular voltage VEB. So that is due to the early effect. And output characteristic, you can see also there is an early effect. VCB, it is a plot of output current versus output voltage, that is IC versus VCB, and VCB is increased. So much increase of VCB will result in the increase in IC, which is due to the again early effect. It is not exactly parallel to each other, and that non-parallel nature comes from the fact of early effect again. And you can see here, before early effect, you can see from a certain region up to a certain region, the currents are equispaced. That is, here the parameter is the emitter current, that is input current is kept constant. Here the 4 values of the emitter current, that is input current, are shown. Emitter current 0, emitter current -4, -8, -12, and you can see the graphs of the collector currents are also equispaced. So it is linearly proportional, that is why it is called linear region of the output characteristic, and this is also known as active region. Okay, because here in this region the emitter base junction is remain forward biased and collector base junction is at reverse biased. And at the left hand side, when the voltage VCB is negative, that means collector is negative with respect to base, that is forward biased. So output collector base junction is forward biased, and here you can see the graphs are very closely spaced. For a very feeble change in the IC, that is the vertical separation is very small with respect to the current. Here the changes, here you can see clearly you can see that the spacings of the graphs. Here you can see for current 0 the graph is here, for current -4 graph is here, for current -8, -12, but here you can see they are very much closely spaced. Yes, they are very much closely spaced, the cross are very much closely spaced. So that is why this region is known as saturation region, and below the current IE is equal to 0, the region is called cutoff. Here both the collector base and emitter base junctions are reverse biased. That is cutoff region, and it is used in the digital circuits to get the zero memory or the zero state. Here it is written. An early effect I have already discussed. So same feature using the CE mode and again using the NPN transistor is depicted here. You can see again the input current versus input voltage, keeping output voltage as constant, but due to early effect the base current decreases here, because the early effect has the characteristic that base current should decrease. It is seen here again, and again the graphs of output characteristics due to the CE mode is shown here. Now to important parameters are alpha and beta of the transistor. What is alpha? Alpha is the current ratio between two currents. One current is that current which is due to the current component of the collector current due to the flow of carriers from the emitter region you can see that collector region has two type of current. One coming from emitter, travels through base and then reaching to collector after recombination. That is the main component, which is called which is actually IC minus ICO, because ICO is the minority current. So that component of current is IC minus ICO. I have already discussed it. Divided by the total emitter current, which has started from the emitter, but the current that reached the collector is IC minus ICO. So that should be less than, this ratio should be less than 1, not maybe the very less than, not maybe, but it should be less than 1. There is another current ratio, it is IC by IB, that is actually the gain of the current, that is collector current by base current in CE mode, and the relation of between those two is very interesting. Starting from IE is equal to IB plus IC, you can write IE in place of IE using the equation of alpha. Here alpha is that, so IE is equal to IC minus ICU by alpha. You can substitute here, and IB, just keep it. And similarly, proceeding in the same way, you can reach up to this point, that is IC is equal to alpha by 1 minus alpha into IB plus ICU by this. Now practically alpha is less than 1, and practically you can take alpha is nearly equal to 0.98. So alpha is in between 0.9 to 0.99. So for this reason 1 minus alpha is very small. So this ratio and ICO is very small with respect to IB also. IB is microampere, but ICO is the minority current is in the order of nanoampere. So you can approximate this equation like this. The second term is cancelled out. So IC is equal to alpha by 1 minus alpha into IB. Now IC by definition IC by IB is beta. So beta is equal to alpha by 1 minus alpha. It is nearly equal to, can be written like this. So you can again find the 1 minus this term and put it back to the actual equation, which is equation number 1. Without any assumption, you can write it like this, and this form of that equation should be remembered because it is very useful equation. And in my next lecture I will discuss the biasing. So biasing will be starting, and I will start it in my next lecture. So in this lecture we have discussed about the transistor, the definition of the transistor, how transistor operates, that's the current component of the transistor, and then the input and output characteristics in the light of some definitions like early effect or other things. And we have also discussed some numerical point of view of the transistor analysis, the current components formula or the formula between alpha and beta. So let me thank you for listening.